An intense atmospheric ridge sits jammed over the continental interior, locking a moisture-laden frontal system across the east coast, while driving temperatures toward dangerous midsummer highs across the plains. Between the Great Smoky Mountains and the Outer Banks, localized rainfall totals are surpassing 250 millimeters over 36 hours, a single, uninterrupted deluge falling on ground already saturated by preceding weather systems. Across the eastern seaboard and central plains, emergency management agencies are tracking multiple flash flood events. Roads have transformed into waterways, low-lying neighborhoods face rapid inundation, and transportation corridors are severed. Yet the primary hazard unfolding along the coast is not an isolated meteorological anomaly or a fast-moving single-day storm. What public headlines frame as a disconnected series of rainstorms and heat waves is a single, unified planetary-scale mechanism, a high-amplitude stationary wave within the upper-level jet stream that has halted the normal west-to-east progression of weather systems across North America. The actual phenomenon driving this multi-regional emergency is a textbook atmospheric blocking pattern, where the jet stream buckles into deep, slow-moving meanders that lock surface features in place for days. It is a continuous thermodynamic engine operating across thousands of kilometers, converting vast reservoirs of tropical moisture into relentless localized rainfall on one flank, while trapping intense heat and manufacturing sequential rounds of severe convective storms along its northern rim. The tension in this setup comes from raw physical numbers and immovable geography. High-resolution numerical weather prediction models have verified widespread rainfall accumulation footprints between 75 and 200 millimeters across eastern North Carolina and southern Virginia, with isolated corridors recording up to 250 millimeters near Cape Hatteras and Kill Devil Hills. To put those numbers into perspective, 250 millimeters represents roughly 2 to 3 months of normal summer precipitation, delivered in little more than 30 hours. When that volume of water hits flat, slow-draining coastal plains or funnels into the narrow drainages of the Appalachian Range, the physical absorption capacity of the soil is breached immediately. Once saturation occurs, every additional millimeter converts directly into surface runoff, driving small creeks past bankful stage and transforming dry channels into high-velocity debris flows. The mechanism governing the relentless coastal rainfall is convective training. Under normal conditions, upper-level jet streams push cold fronts rapidly across the continent, delivering brief, manageable showers. But when the jet stream buckles into a high-amplitude wave, the surface boundary stalls. Thunderstorms initiate along this line and move parallel to the front itself. Rather than passing over a town and moving on, successive storm cells track over the exact same geographic location in continuous sequence, like individual cars on a freight train. The total rainfall at any monitoring station is the cumulative output of hours of deep convection stacked back-to-back over the same coordinates. Compounding this stagnation is the sheer volume of precipitable water being fed into the system. Hundreds of kilometers to the southwest, Tropical Storm Bertha made landfall near the Gulf Coast, with modest sustained winds of 75 kilometers per hour. While its wind field posed minimal threat to structural infrastructure, its thermodynamic signature carries an immense plume of precipitable moisture drawn directly from maritime tropical air masses. As high-pressure ridging and upper-level wind shear dismantle the organized convective core of the tropical system near the coast, that massive reservoir of moisture is redirected. The stalled frontal boundary to the northeast acts as an atmospheric conveyor belt, tapping into the tropical moisture plume and directing it straight into the mid-Atlantic and Appalachian regions. The worst surface flooding is thus occurring over 1,000 kilometers away from the storm's center, where the moisture plume intersects the stationary front and steep mountain topography. In the high terrain of western North Carolina and eastern Tennessee, where rainfall totals are reaching 200 millimeters, the hazard profile is amplified by historical land degradation. This is the same mountain terrain that suffered catastrophic slope failures and valley scouring during Hurricane Helene in 2024. Heavy rainfall on mountain slopes funnels surface runoff into narrow V-shaped valleys, accelerating water velocities and picking up loose rock, trees, and uncompacted sediment. When 200 millimeters of water falls on river basins whose channel geometries were permanently altered and whose hillsides remain structurally compromised, the threshold for destructive flash flooding flooding and debris flows drops significantly. Soil profiles that are already fractured absorb less water, sending massive surges of mud and timber directly into downstream communities. Meanwhile, on the opposite side of this stationary wave, a completely different hazard is being manufactured by the exact same jet stream configuration. As the trough holds firm over the eastern seaboard, an immense ridge of high pressure, a heat dome, is expanding across the continental interior. Underneath a high-pressure ridge, descending air compresses and warms adiabatically. This large-scale subsidence suppresses cloud formation, allowing intense solar radiation to bake the land surface day after day. In urban centers and agricultural heartlands alike, surface temperatures climb well above seasonal norms, straining electrical distribution grids as cooling demand spikes, while elevated nighttime low temperatures prevent human bodies and livestock from shedding accumulated heat stress. Yet the heat dome does not merely produce static high temperatures. It functions as a critical atmospheric boundary. The high-pressure ridge acts like an immovable physical barrier in the middle troposphere. Weather disturbances moving around the circulation cannot push through the high-pressure core, so they are forced to track around its northern and eastern perimeter. This outer edge becomes a high-velocity convective corridor. Warm, highly unstable air near the surface, rich in low-level moisture, interacts with shortwave disturbances passing aloft along the rim of the dome, triggering organized lines of severe thunderstorms. Over the coming 72 hours, this setup is projected to execute a sequential, multi-day severe weather corridor. On Sunday, a deepening surface low dropping to roughly 995 millibars over the northern plains will initiate severe convective cells across Nebraska, Iowa, Minnesota, and Wisconsin, bringing threats of damaging straight-line winds, large hail, and isolated tornadoes. By Monday, as the upper-level shortwave slides eastward along the crest of the heat dome, the severe weather envelope shifts directly into the Great Lakes, the Ohio Valley, and southern Ontario, where steep lapse rates and strong deep-layer shear will support organized squall lines and supercells. By Tuesday, the same system advances toward the eastern seaboard, threatening major urban transit networks from the mid-Atlantic up into New England. 3 consecutive days of severe convective storms hitting nearly the same regional corridors is the definitive signature of a locked jet stream pattern, compounding structural damage, exhausting municipal recovery resources, and dropping additional rainfall onto river basins operating at maximum capacity. Which brings us to the central unifying question. How does a single stalled wave in the upper atmosphere simultaneously drown one region under record tropical rainfall, bake the continent's interior under an immovable heat dome, and fire sequential rounds of severe storms across the northern plains and Great Lakes? And what specific atmospheric indicators will signal that this destructive planetary loop is finally breaking down? A single digital precipitation counter on a hydrometric station along the Appalachian foothill boundary registered 0 millimeters of rainfall at dawn on a midsummer morning, exactly 48 hours before its internal data logger recorded a continuous inundation exceeding 250 millimeters. That stark contrast between absolute dry ground baseline readings and rapid environmental saturation illustrates how fast a localized weather regime can breach established engineering tolerances. Across the Central Plains, through the Great Lakes Basin, and along eastern transit corridors, modern infrastructure was built under specific historical assumptions. Civil engineers, municipal flood planners, and grid operators designed stormwater networks, culvert capacities, and transmission systems around historical return periods. Statistical benchmarks derived from decades of observational data collected by agencies such as Environment and Climate Change Canada and the Meteorological Service of Canada. For nearly a century, these models assumed that severe convective storms, tropical moisture plumes, and regional heat waves were distinct, transient events bounded by predictable seasonal limits. Popular media frame these summer weather disasters as isolated, record-breaking storms that simply outgrew local infrastructure. Correcting that loose framing reveals a far more critical reality. The current emergency is not defined by one extraordinary thunderstorm, but by a fundamental breakdown in the atmospheric circulation patterns that historically kept weather systems moving across the continent. When a jet stream pattern buckles and locks into place, historical statistical baselines used to design municipal stormwater systems become instantly obsolete. To understand why this structural shift is so dangerous, one must examine how the North American climate system functioned under normal parameters. Historically, the polar jet stream operates as a high-altitude, fast-moving river of air flowing west to east across mid-latitudes, driven by the temperature gradient between the Arctic and the equator. In a balanced system, this upper-level current acts as a conveyor belt, sweeping surface troughs, low-pressure centers, and convective storm lines across provinces and states at a steady rate of 30 to 50 kilometers per hour. A typical summer frontal pass would deliver 20 to 40 millimeters of rain over a localized watershed in 3 to 4 hours before clearing out to the east, allowing local river systems, drainage channels, and municipal storm sewers to discharge runoff safely into regional lake basins or coastal estuaries. Historical benchmarks established during the mid-20th century, such as regional drainage designs implemented following major disasters like Hurricane Hazel in October 1954, were engineered around these transient dynamics. Municipal infrastructure across North America was explicitly calibrated to handle brief, high-intensity precipitation spikes, followed by prolonged dry intervals during which soils could drain, water tables could stabilize, and natural channel geometries could recover. The baseline return period for what meteorologists designate a 1 in 100-year storm event was calculated on the premise that intense convective rain cells would remain mobile. When a storm system moves across a watershed at 30 kilometers per hour, the precipitation footprint is distributed across hundreds of square kilometers, preventing any single drainage basin from receiving the entirety of the cloud mass's precipitable water. The current pattern has completely upended that mechanical baseline. By forcing a high-amplitude Rossby wave to grind to a halt, the atmosphere effectively eliminates the translation speed of surface fronts. Instead of traversing 3 provinces in 24 hours, a stalled boundary remains fixed over a single corridor, directing a continuous stream of tropical moisture straight into localized watersheds. When 200 to 250 millimeters of rain falls on a single drainage basin within 36 hours, a volume equivalent to roughly 25 million liters of water per square kilometer, it overwhelmingly surpasses the design capacity of urban culverts and retention basins, converting engineered drainage corridors into unmanageable flood channels. Furthermore, the baseline for regional heat waves across the continental interior was similarly bounded by atmospheric mobility. Historically, high-pressure ridges over the Great Plains would build, mature, and eventually be displaced within 3 to 4 days by an advancing upper-level trough originating over the Pacific Northwest. Thermal energy stored within the lower atmosphere was routinely vented by these passing cold fronts. Under the current locked regime, the heat dome remains stationary, trapping solar radiation and compressing descending air over millions of square kilometers. This prolonged heating creates an extraordinary reservoir of convective available potential energy, charging the atmospheric battery along the northern and eastern margins of the dome. When shortwave disturbances pass over this stationary thermal boundary, they trigger repeat lines of severe thunderstorms that track along the exact same path day after day, a destructive mechanism that directly threatens transboundary water systems monitored by the International Joint Commission and regional power utilities like Hydro-Quebec and Ontario Power Generation. Today's multi-regional crisis is not an unpredictable act of nature, but the direct result of a structural failure in atmospheric movement, testing the absolute physical limits of North American infrastructure. 3 separate monitoring stations across North America, a coastal stream gauge registering a rapid stage rise in eastern North Carolina, a radiosonde atmospheric sounding launched near Kansas City showing unprecedented precipitable water levels, and a surface weather station in southern Ontario recording a sudden 9 millibar pressure drop, were all responding to a single underlying physical anomaly. What connects these disparate observations is the precise mechanical breakdown of planetary-scale atmospheric circulation. Popular reporting frames these distinct crises as an unlucky coincidence of isolated weather systems hitting different parts of the continent simultaneously. However, correcting that surface-level narrative reveals a far more rigorous physical mechanism, a stalled atmospheric blocking pattern where the mid-latitude jet stream undergoes extreme wave breaking, pinning surface weather features into stationary positions and converting a routine thermodynamic setup into a persistent hazard engine. Understanding the physics of this failure requires looking at how energy moves through the upper atmosphere. Under normal dynamics, the jet stream operates as a geostrophic wind at an altitude of 9 to 12 kilometers, maintaining its west to east path due to the temperature differential between polar regions and the tropics. When that thermal gradient weakens or distorts, the jet stream loses zonal momentum and meanders, forming high-amplitude Rossby waves. When these waves reach extreme amplitude, they undergo wave breaking, detaching from the main zonal flow to form a closed, stationary block. In this specific event, a massive omega block has anchored itself over the continent's interior. On the eastern side of this block, an upper-level trough has dug deep into the eastern seaboard, creating a stationary surface frontal zone extending from the Gulf Coast directly up into Atlantic Canada. Simultaneously, the western flank has locked a strong upper-level ridge directly over the central plains. The physical mechanics that transform this stalled front into a flash flood driver rely on three distinct factors: moisture advection, convective training, and topographical forcing. First, the stationary front acts as a thermodynamic vacuum. Hundreds of kilometers to the southwest, the remnants of Tropical Storm Bertha, a system whose core convective structure was sheared apart near the Gulf Coast, continue to pump massive quantities of tropical moisture into the lower troposphere. Rather than remaining localized, this moisture plume is drawn northward along the boundary of the stalled front. The atmospheric moisture content, measured as precipitable water by Doppler radar networks and satellite radiometers operated by agencies such as Environment and Climate Change Canada, has reached extreme values exceeding 60 millimeters, nearly double the climatological average for this time of year. Second, because upper-level steering winds are oriented parallel to the stationary surface front rather than across it, individual convective thunderstorm cells forming along the boundary travel along the exact same linear vector. As one cell discharges its moisture over a catchment area and dissipates, the cell directly behind it tracks into the exact same coordinates, producing convective training. Cumulative precipitation over any single square kilometer is not the result of one passing storm, but the sum of 10 or 15 consecutive storm cores passing over the same ground in succession. Third, when this atmospheric fire hose encounters physical landforms, such as the steep escarpments of the Great Smoky Mountains and the broader Appalachian chain, orographic lifting forces the saturated air mass to ascend rapidly. As air rises along mountain slopes, it cools at dry and saturated adiabatic lapse rates, causing immediate condensation and forcing immense volumes of water out of the air mass. In basins previously scarred by major hydrological disasters, such as western North Carolina following Hurricane Helene in 2024, the structural capacity of the landscape to absorb this deluge is essentially zero. Saturated soils lose shear strength, converting topsoil into liquid mud, while altered river channels offer no resistance to rapid stage increases. Meanwhile, on the opposite side of the atmospheric block, the physics of the heat dome operate through thermodynamic compression. Beneath the core of the upper-level ridge, strong, large-scale air subsidence occurs. As air sinks through the troposphere, it compresses under increasing atmospheric pressure, heating up at the dry adiabatic lapse rate of approximately 10 degrees Celsius per 1,000 meters of descent. This sinking air mass acts as an invisible lid, preventing vertical air motion and suppressing cloud development. Without cloud cover, solar radiation strikes the Earth's surface unimpeded, elevating daytime temperatures and drying out surface soils. This creates a positive feedback loop. Dry soils can no longer dissipate heat through evapotranspiration, forcing all incoming solar energy into sensible heating, which further warms the lower atmosphere and strengthens the high-pressure ridge above. The breaking point of this system occurs along the outer boundary of the heat dome, the baroclinic zone, where the hot, buoyant air mass trapped under the ridge collides with cooler, denser air masses moving around its northern perimeter. This boundary zone accumulates immense convective available potential energy, often exceeding 3,000 to 4,000 joules per kilogram. When small upper-level shortwaves traverse this boundary, they act as mechanical triggers, releasing stored energy in explosive, organized severe weather outbreaks. Instruments confirming this locking mechanism, from radiosonde soundings and geostationary satellite imagery to Canadian Hazards Information Service monitoring networks, show that until a major high-momentum polar trough enters the system to break the omega block, this planetary engine will continue continue to cycle heat, flooding, and severe storms across the same regions day after day. A red priority alert broadcast across Public Safety Canada's National Alert Ready system landed on thousands of mobile devices at 8:14 Eastern Daylight Time, warning residents in flood-prone corridors that local watercourses were exceeding historical high water marks. That single digital notification represents the precise threshold where large-scale atmospheric physics intersects with daily human life. When a locked Rossby wave maintains a stationary atmospheric boundary over North America, the resulting physical impacts cascade directly into critical infrastructure, supply chain corridors, and municipal power grids. Public discourse often frames the impact of severe weather as a series of inconvenient property cleanups or temporary travel delays. Correcting that superficial view reveals a far more systemic vulnerability. Our modern integrated economy relies entirely on the assumption of atmospheric mobility. When weather stops moving, physical systems designed to support millions of people begin to fail in structured, predictable stages. Consider the immediate consequences unfolding along eastern transportation corridors. The continuous accumulation of 200 to 250 millimeters of rainfall over 36 hours does not merely submerge local residential streets, it saturates the structural subgrade beneath regional rail lines and major interprovincial highways. When ballast washes out beneath main rail corridors, primary freight movements carrying essential bulk commodities, agricultural yield, and manufactured goods grind to an absolute halt. On major highway networks, moving water just 50 centimeters deep exerts enough lateral hydrostatic force to sweep heavy vehicles off roadbeds, forcing transport authorities to issue emergency closures. To visualize the physical volume involved, 250 millimeters of rainfall distributed across a medium-sized county equates to more water than the entire annual domestic consumption of a city of 1 million people, delivered onto saturated ground in a single day and a half. With nowhere to drain, this water collects in primary valleys, threatening water treatment plants, submerging electrical substations, and cutting off power to tens of thousands of homes. Furthermore, the cascade extends directly into transboundary environmental and economic systems. As the heat dome intensifies across the continental interior, resulting thermal loading places immense mechanical stress on energy infrastructure. High ambient temperatures force residential and industrial cooling systems to run continuously at peak capacity, driving electrical demand toward historical grid thresholds. In major energy markets managed by regional transmission operators and provincial utilities such as Hydro-Quebec and Ontario Power Generation, high surface temperatures reduce the operating efficiency of thermal power plants while causing high-voltage transmission lines to sag under heavy load. When a thermal ridge locks temperatures above 35 degrees Celsius for 5 consecutive days, soil moisture in agricultural regions such as the Canadian prairies and the American Midwest evaporates at accelerated rates. Irrigation reservoirs such as Lake Diefenbaker along the South Saskatchewan River system experience rapid drawdowns, threatening both municipal intake elevations and regional crop yields. Along the boundary zone where the heat dome meets cooler northern air masses, the sequential 3-day severe weather corridor presents an escalating compounding risk. When severe convective storms track across the Great Lakes Basin and the St. Lawrence Lowlands on Sunday, Monday, and Tuesday, the damage is cumulative. The first wave of severe thunderstorms, producing localized straight-line winds in excess of 100 kilometers per hour, weakens urban tree canopies and damages primary distribution lines. The second wave, hitting 24 hours later, strikes communities where repair crews are still actively working to restore basic utilities. By the third day, emergency services are stretched to capacity, municipal backup generators run low on fuel, and regional soils are so thoroughly saturated that even moderate wind gusts easily uproot mature trees, causing widespread multi-day blackout events. This multi-regional escalation demonstrates that a locked atmospheric pattern is an active force multiplier systematically destabilizing engineered networks. 3 distinct observational readings, a geostationary satellite water vapor imagery loop over North America, a 500 millibar geopotential height analysis chart from Environment and Climate Change Canada, and an automated stream stage hydrograph in the Mid-Atlantic, are all currently pointing to the exact same physical reality. As this atmospheric episode matures, establishing the precise boundary between verified meteorological mechanics and unresolved system variables is essential for maintaining analytical credibility. What is firmly established by observational networks and numerical weather prediction models is that an atmospheric blocking pattern has anchored itself over the continent. The stalled frontal boundary across the eastern seaboard, the massive moisture export originating from the remnants of Tropical Storm Bertha near the Gulf Coast, and the expansion of an intense high-pressure ridge across the continental interior are all verified physical components of a single, highly unified system. Furthermore, the mechanics driving the multi-day severe weather corridor from the Midwest through the Great Lakes and into the St. Lawrence Valley are well understood. Upper-level shortwave energy riding along the northern perimeter of the heat dome will repeatedly trigger organized convective systems over saturated watersheds. What remains genuinely unresolved, however, is the exact temporal horizon for pattern breakdown. Global forecast ensembles, including the European Center for Medium-Range Weather Forecasts and the Global Deterministic Prediction System, continue to show significant spread regarding when a high-momentum polar trough will finally penetrate the block and restore normal zonal flow across the mid-latitudes. Until that wave transition occurs, the atmospheric machine remains locked in place, actively reloading its convective potential. To track how this situation unfolds over coming days, there are 3 specific checkable indicators every observer should monitor on official forecast charts and surface observation networks. First, monitor the 500 millibar height contours across the Pacific Northwest and Western Canada. A progressive, high-amplitude trough entering British Columbia would indicate the arrival of sufficient kinetic energy to kick the stationary block eastward. Second, track the 700 millibar temperature profile along the northern rim of the central ridge. If mid-level temperatures begin to cool, the atmospheric cap holding the heat dome in place will weaken, reducing the intensity of the severe weather corridor tracking toward the Great Lakes. Third, watch primary stream gauges managed by national hydrometric networks along the Appalachian Chain and Mid-Atlantic transit corridors. A cresting and sustained drop in river stages below bankful levels will signal that the moisture plume from the Gulf has finally been severed. Until one of those 3 physical markers is observed, the default operational reality remains unchanged. The stalled jet stream will continue to cycle heavy rainfall over saturated eastern catchments while driving intense heat and sequential severe storm outbreaks across the continental interior. We are not dealing with a series of disconnected summer storms, but with the immense, unyielding physics of a stationary atmosphere. Let us know in the comments where you are watching from today and what conditions you are seeing on the ground. If you value precise, mechanism-driven analysis of major geographical and infrastructure events, hit the subscribe button to stay informed as this situation develops.